So earlier today, my friend Travis and I were playing a game of quarters. Well, actually it wasn't quarters, we didn't have a quarter, so instead we played Euros. And during this rousing game of Euros, we came to the realization that inevitably we would no longer be able to keep the Euro spinning. So we did a little physics experiment over the law of conservation of angular momentum to keep the Euro spinning. Let's take a look at the video. Oh! Gosh dang. A little bit. Game face on. Ah, yeah. Ah, yeah. God, this sucks. Yeah, you know, Trav, if it wasn't for the friction on this table, the law of conservation of angular momentum would keep this Euro spinning continuously.
Really?
Yeah.
What's the law of conservation of angular momentum?
Let me tell you about it.
All right.
Over here. Yeah, have a seat right there, Trav.
Right here?
Yeah, you can take some notes, whatever.
Oh, that's cool.
So listen, my man, in the law of conservation of angular momentum, so we have here, L equals your angular momentum equals I, which is the moment of inertia, times omega. I equals mass times radius squared, that's your moment of inertia, where omega is your angular velocity, which is 2 pi frequency. In angular momentum, the total angular momentum of a rotating object remains constant if the net torque acting on it is 0. Let's take the Euro for example. Okay. Whoops. Can I try that again? Thanks, man. Okay. As the Euro spins, if it wasn't for the friction acting on it, it would continue to spin at the same rate because there's no net torque.
Wow, Nate, that's really interesting. Are there any other aspects you can tell me about for the law of angular conservation momentum?
You mean the law of conservation of angular momentum?
That one, yes.
Yeah, of course, Trav. If the net force acting on a rotating object is 0, that its angular momentum stays the same. So as we said, L is angular momentum. That means if I, which is the moment of inertia, changes either because of the mass or the radius changes, then the angular velocity, which is omega, will compensate for it, either speeding the object up or slowing it down. The angular velocity, that is. So let me show you here. So if we have, this will be our moment of inertia, it'll be mass times radius squared times omega. If our radius is, say, like a meter, and we change that to 0.5 meters, then omega will speed up, the angular velocity will speed up to compensate for the moment of inertia going down. It'd be easier if we use the chair to explain. Okay, Trav, leave your arms out, okay? I'm going to give you a big spin. Ready?
Got it.
Okay, pull your arms in. Did you feel yourself speed up?
I felt that.
Awesome.
Okay, so Nate, I felt myself speed up. I don't understand why though. Can you explain that to me?
Yeah, I can. So Trav, the reason you sped up was because the angular momentum has to remain constant in your isolated system. So because there was no net torque acting on you, were an isolated system, you were spinning by yourself, the only thing that changed, of course your mass didn't change, you didn't lose any weight, but the radius from your arms out came in, the radius went down. And so L has to stay the same. So basically we just make up some numbers here. Let's say that this all together, if you multiply those together, let's say like 5, and this was 4, this is being your angular velocity, would equal 20 altogether, right? Let's say this moved down and the radius now went to 4. This has to now go to 5 to keep this still at 20. So remember this, the angular velocity is how fast you're rotating. In order to keep the angular velocity the same, your body has to take on the extra velocity to compensate for the change in rate. So what do you think, Trav?
I think I get it. It's the law of conservation of angular momentum.
That's right, Trav. Awesome.
I got it.
Now, Trav, there's one other implication of this law that we haven't gone over yet.
What is that, Nate?
It's not a spinning euro, that's for sure. But let's say we take this same law and apply it to the Earth as a whole, as the Earth is spinning about its axis. Now, the moment of inertia for the Earth is 2 over 5 times the mass of the Earth times the radius of the Earth squared. Okay? Now let's say if we were to take the angular velocity times this number, which for the Earth, we can plug in the mass of the Earth times the radius of the Earth. Let's say if we were to take the Earth as a whole and launch a whole bunch of space shuttles off the Earth at the same time, taking away from the mass of the Earth. What do you think would happen, Trav?
I don't know. Why don't you tell me?
Okay, let's draw this out. So let's say, for example, Trav, we have 10 spaceships, space shuttles, all situated around the globe in 10 different locations. And these are very massive spaceships. They're big suckers. You know what I'm saying? Anyway, so if you have these all situated around the globe in different locations and we launch them simultaneously at the same time, then this is taken away from the net mass of the Earth. The angular momentum, once again, like we said, if the mass goes down, the omega, the angular velocity, has to speed up to compensate that the angular momentum will stay the same. So let's watch and see what happens. We're going to launch these shuttles. Sorry, stop. Did we already do that before?
Law of conservation of angular momentum.